Let us start this lecture with a thought process. Success and failure are two perpetual processes that are encountered on the path of human life. Hence, there is no need to be either related or perturbed by its manifestation. So, if you recall that in the last lecture, we discussed about the partial derivative method and Jacobian methods, and we have recapitulate the rules which govern this partial derivative method. There are basically three rules. One is the reciprocal rule, chain rule, and the what you call cyclic rule. So, these three are to be used, and then later on we also find out the relations, how to connect these Jacobians with the partial derivatives, and we have also enumerated the four rules. And later on we looked at the thermodynamic potential. We discussed about four potentials, basically internal energy, enthalpy, Gibbs function, and Helmholtz function or potential, whatever you call. And we also derived the relationship, connecting those change in the potential, thermodynamic potential in terms of measurable properties and non-measurable properties, right? And those things we will be now connecting it, with the measure and non-measurable properties. So, in today's lecture, so let us consider a thermodynamic potential, that is internal energy, which is more natural because it comes from the first law of thermodynamics, whereas other properties are derived, right? And for which we can write down, that is the first Gibbs equation, that is du is equal to Tds minus Pdv, and u as we know is basically thermodynamic properties, and hence its differential must be exact, and for that what we will do, we will use this condition, that is dou m by dou y when x is equal to constant equal to dou n by dou x when y constant, if the form is basically m dz is equal to m dx plus n dy. There is a lot of similarities between this and also this one, right, isn't it? And if you look at in this case, in this equation 1, the m is basically t, and in equation 2 you can say n is equal to minus p, right. So, I can write this condition like for to a property like internalized property as basically dou t by dou v when s remaining constant is equal to minus dou p by dou s when v is remaining constant. So, if you look at basically this one, what it indicates, if you look at left hand side, that is basically change in the temperature with respect to specific volume, whereas right hand side change in pressure with respect to entropy. As we know that entropy is not a measurable property, right, whereas temperature, volume, pressure are measurable property. That means I can relate the non-measurable properties with the measurable properties with this expression, right. Okay. And this expression is basically known as the Maxwell relation. It is a very important aspect which is being used in thermodynamics, particularly for having the thermodynamic relations. The objective of thermodynamic relation is to connect the non-measurable properties with the measurable properties. So, in the similar manner, we will be using others Gibbs equations, right. There are total 4 Gibbs equation we have seen or we have derived in the last lecture. So, we will be using that. So, let us look at what are the thermodynamic potential we have discussed till now. That is, one is internal energy, right, and which is a function of S and V, right, isn't it? If you look at this from this equation, you can write down U is a function of S and V. And by using this U as a property of the system, then I can find out this expression very easily, right, and that is the differential, and this being derived from the differential relationship, what we call Gibbs equation, that is equation number 1. So, we can, this equation is basically Maxwell equation. In similar manner, right, I can write down that change in the Helmholtz function is equal to minus S dt minus P dV. We have already derived this. And by using the same condition, I can get dou S by dou V when temperature remaining constant is equal to dou P by dou T when volume remaining constant. If you know this expression, right, differential expression, very easily you can get a Maxwell relationship, right. In the similar fashion, we can write down that dH is equal to TdS plus VdP, right. And from this expression, I can write down dou T by dou P when entropy remaining constant is equal to dou V by dou S when pressure remaining constant. If you look at, all are trying to connect entropy with respect to the rest of the what you call measurable properties like pressure, temperature, specific volume. So, in the similar fashion, I can get dz is equal to minus S dt plus V dP, and from this I can get, that is, dou S by dou P when temperature remaining constant is equal to minus dou V by dou T when pressure remaining constant. So, these four are basically the Maxwell relations, right, and this is in the differential form. But I want to write down in Jacobian form what it would be, right. It will be very simple one, right, okay, and that is basically Jacobian PV is equal to Jacobian TS. You can say with respect to PR or any other thing, right. So, is it true? Right, and this is a very important expression, these Maxwell relations, because that you can connect the non-measurable properties to the measurable properties. And coming back to that, like this Jacobian form is a very simple and very easy to remember, like let us consider this one, right. If I consider the first one right here, what I can write down? I can write down T S V S is equal to minus P V into S B, right. So, is equal to, can I write down this way, that is P V into V S, can I write down? It is very easy, I am just changing, this negative has has gone out because I have interchanged these variables here, right. So, therefore, I can write down very easily, that is PV, Jacobian PV is equal to Jacobian TS. Yes or no, right. Similarly, I can take another one, let us say this one I am taking now, right. I can write down S T Jacobian PT is equal to minus Vp and Tp, right. Similar way, I can write down this, right, this as basically if I write down, I can write down Vp, right, equal to Pt, can I, and negative sign has gone, right. So, can I write down this as St I can also write down as Ts, okay, Ts here into Pt minus is equal to minus Pv into Pt. Yes or no? So minus minus will cancel it out. So I will get basically Ts is equal to Pv Jacobian. So the same thing I am getting. So all these things you can see, all four Maxwell relation, right? All these four Maxwell relationship can be converted into one equation in case of Jacobian form. So that is very easy to remember and handle, we will see. So and also you can think of mnemonic diagrams, which you definitely might have used, like in your earlier days to remember certain things, like Maxwell relation can be easily written in the diagrammatic form. Like, I can think of putting this in a anti-clockwise. If you look at this one here, right, A, G, H, U, this is alphabetical order, and these are all what you call potentials, right. And we know that A is basically a function of V and T, you can write down here. Similarly, G is a function of T and P, this is basically capital P, okay, pressure. And H is a function of entropy and P, and U is a function of S and B. And of course, this is a what you call, as I told that this potential A, this is potential, right? This is basically thermodynamic potential, right? A, G, H, S are placed in anti-clockwise. This is in a clockwise, placed in clockwise direction, right? Because this is the clockwise, and it is flanked by their what you call functions or the independent the variables. Right, and now I can write down the Gibbs equation, very easily. Like du, I am taking an example, is equal to sine into coefficient into ds, and also I will have to use sine and coefficient v. So if I take that, this u, if you look at, u is basically, the independent variables s and v. So if you look at the sine and the coefficient for s will be t. If it is in this direction, direction of the arrow, then it will be positive sign. So this I can say positive sign. And what will be coefficient here for du? It will be basically t. The coefficient is t. Similarly, and sign for this, v, because it is on the opposite direction of the arrow. So therefore, it will be negative sign, and coefficient will be p. So if you look at this is ds, dv, and is equal to du. So you can write down this basically du is equal to t ds minus p dv. This is the Gibbs. If you can remember it is fine, otherwise also this is the helpful, this diagram will be helpful to remember you, keeping the sign in this. So similar way I can have, of course once you know this relationship, I can very easily find out Maxwell relation, right? Dou t by dou v s is equal to minus dou p by dou s, v is remaining constant, right? And we can, from this diagram, we can have a relationship dH is equal to TdS plus VdP. Let me just tell you again how, because if you look at H is having two independent variable, one is S and other is P. So if you look at that for the S, the coefficient will be T, right, and it will be positive. So therefore this is positive T. And in this case, for the P, the coefficient is V, it is also positive. So therefore it is dH is equal to TdS plus VdP, right. And you can get the Maxwell relation very easily, and similar way you can have the Gibbs function. And if you look at Gibbs function is basically two independent variable, one is P and T. If you look at T, the sign will be, in this case, what it will be? It will be negative, and the coefficient will be S. So, therefore, it is a negative here, right. Therefore, it is a negative sign here. And of course, for the P, that is the V, it is in the same direction of the arrow. So, therefore, it is positive. In similar way, we can also look at the Helmholtz function, and that is equal to dA is equal to minus S dt minus P dV, and you can get a Maxwell relationship. So, if you look at, this is the way how you can remember this Maxwell relationship, so that you can utilize for solving the problems very easily. And we will look at basically thermodynamic relations, right. And of course, for that we need to use some more properties apart from PVT, and those are Cp, Cv, beta. Beta, like it is the coefficient of volume expansion, K, that is the isothermal compressibility, and we know that coefficient of volume expansion is beta is equal to 1 over V into dou B by dou T when pressure remaining constant. So, I can write down that in the Jacobian form, that is 1 over V is equal to Jacobian Vp with respect to Tp, right, just to convert that partial derivative into the Jacobian form. In the similar way, isothermal compressibility K, which is equal to minus 1 over V into dou B by dou P when temperature remaining constant, and is equal to 1 by V into Jacobian Vt with respect to Pt. So, if you look at, sometimes you keep in mind, I use this isothermal compressibility. Sometimes I use Kt, okay. You just check, I mean Kt and K are same, right, that kind of things you can keep in mind. So, beta by K you can think of, like you can just divide that equation. This, if I say this is equation 1, right, and equation 2, you can get beta by K is equal to dou B by dou T pressure remaining constant into dou P by dou V T, of course, with a minus sign. And you can apply this cycle relationship, and you can find it out basically, that is equal to, you can simplify this expression, right, as dou P by dou T into V using the cycle relationship, right. And by definition we know Cv is equal to dou U by dou T when volume remaining constant, and that is equal to du by dt. And we know that du is equal to Tds minus P dV, right. So, we can use that, and when dV is constant, that is nothing but your Tds, Tds is equal to du. And I can write down that in place of like Cv is equal to dou S by dou T when volume remaining constant is equal to T Jacobian Sv with respect to Tv, right. Because in place of this dou U, you can utilize this expression, right, very easily. In the similar way, we can also express in the Cp in terms of entropy, that is Cp is equal to T dou S by dou T when pressure remaining constant, and right. So, you can basically can write down Cp is a function of S and T, and similarly Cv is a function of what you call S and T. So, if you look at like these are the guidelines I would like to give how you will handle the thermodynamic relations. First you express the partial derivative in terms of Jacobians, right. That is the easier way. And if thermodynamic potential U, H, A, G appear in the expression, replaced by the differential expression, like for the all Gibbs Gibbs equation we have derived 4 equations. And if S appears in the expression, you eliminate that by using Maxwell relations or Cp or Cv, and final expressions would contain only the measurable properties, and those are P, V, T, and then beta, K, Cp and Cv. So, these are all measurable properties. So, therefore, you should do that. And I will tell you, like, you can use both Jacobian and partial derivative, or you can use the partial derivative itself, like alone. And Jacobian will be very helpful, and it will be very faster also in deriving the expressions. So, let us look at some kind of how we can derive the relationship. We will first consider the entropy change, which is this thing. So, we have seen that entropy is a function of T and V, where Tv are the independent variables, right. And we will use the partial derivative method, that is ds is equal to dou s by dou t when volume remaining constant into dt plus dou s by dou v for constant temperature into dV, right. And if you look at this is your first term is the m, and you can say this is n, then you can very easily find out what it would be, right. So, if you look at the recall, this one, the Cv is basically dou s by dou t v, right, into t. So, therefore, I can replace this term, I can replace this term basically by Cv by t, right, very easily. And we need to also look at dou s by dou v when temperature is remaining constant, and from Maxwell relation we know dou s by dou v t is nothing but your dou p by dou t for constant volume, right. That we can use here Maxwell relations. So, if we will use this one, I can get that ds is equal to Cv by t into dt plus dou p by dou t when volume remaining constant into dV, right. That we have already replaced this thing. So, if you look at all these things are basically right hand side, changing right hand side are what you call measurable properties, right. And whereas the entropy change can be expressed in terms of measurable properties like Cv, pressure, temperature, volume, all those things. So, then it will be easier, and we can write down Tds is equal to Cv dt plus T beta by k. We have already derived this expression, right. Beta by k is nothing but your dP by dTv in the last this thing earlier we have done that. So, therefore, this expression is basically now in terms of all measurable properties. Okay. So, by the Jacobian method, we have done the partial derivative, means without really invoking the Jacobian method, you can do that. But in the partial derivative, we will do it just to illustrate that. The equation 1 can be written as the ds is equal to Jacobian Sb with respect to Tv into dt plus Jacobian St with respect to Vt into dV. And we know this Sv and Tv basically Cv by T, that is we already know Cv is equal to T and what you call Jacobian Sb with respect to Tv. So, therefore, I can write down here very easily Cv by T, and here in this expression if you look at it is basically what you call St. We know by the Jacobian, that is Pv Jacobian is equal to Ts, right, by the Jacobian method from the Maxwell relationship. So, I can do that easily, right, and therefore, that became PV, and if you look at, I can write down here instead of ST, I can write down what you call Vp, and then I will take, I can, in place of this, I can write down as basically what you call minus PV, I can write down minus PV here, and Vt is there. If I change it, this become, if I say this is T and this V, then this become minus and minus, so it will be plus. So, that is nothing but your beta by k, right. And then I can get the very easily ds is equal to Cv by T into dt plus beta by k dV, right. And we can put that expression, Tds is equal to Cv dt plus T beta divided by k into dV, and this is the same expression what we got earlier by the partial derivative methods, right. So, if you look at this is little faster way of doing, you need not to remember which relationship we will be using, which Maxwell relationship we will be using. In this case, when we do by the partial derivative, I will have to look at it, and also of course, one can say because the entropy with the volume with temperature, then it has to be converted into expressed in pressure and temperature when volume remaining constant, but you will have to remember. But here it is very easy, simpler way of doing the what you call Jacobian method, because of the fact that the Maxwell relation can only one, not four, as in the case of partial derivative. Let us consider the relation form u is equal to Tv, right, and so I can write down d is equal to dou u by dou Tv into dt, and plus dou s by dou v when temperature remaining constant into dV, and so that we can also express in terms of Jacobians. And if you look at this thing, we already know from the what you call first Gibbs equation, and this expression is nothing but your what you call dou u by dou Tv is T, and whereas minus P is basically dou S by dou V T, that one. So, and of course, for this you can find out from this first Gibbs equation, you can express in terms of Jacobian, that is Jacobian u v is equal to T S V minus P Jacobian V b, and Jacobian V b we know it is 0, right, by the Jacobian rules. So, therefore, the Jacobian u v is nothing but T into Jacobian S b. Similarly, we can write down u with respect to T from this expression, that is Jacobian u t is equal to T into Jacobian S t minus P Jacobian V t. And then we can write down basically equation 1 as du is equal to Sb and with respect to Tv into dt, plus in place of what you call dut by Vt, I can write down that from this expression I can write down basically as ut Jacobian Vt is equal to T Jacobian St Vt minus P Vt Jacobian by T. So, this is cancelled. So, you get basically T as Jacobian with respect to Vt minus Pv. So, you can get very easily. And this expression is basically Cv, this is nothing but your Cv. And this we need to look at it, and that is nothing but your beta by k, right? And we can use the Maxwell relations here and then get that one, because Maxwell relation is Ts is equal to Pv. So, therefore, we can replace this term with the Maxwell relationship, and then after that connect to the beta by k. So, therefore, we can get du is equal to Cv dt plus T beta by k minus P into dV. So, this is the expression change in internal energy in terms of all what you call measurable properties like Cv, temperature, coefficient of volume expansion, isothermal compressibility and pressure, right, and also the specific volume. So, all these are measurable properties, and we can connect very easily evaluate the change in internal energy. And for an ideal gas law, we know beta is equal to 1 by T, and the K, that is isothermal compressibility, is equal to 1 by P. So, if I put it here, beta by K become basically P by T. Instead of this, I can write down T. So, this cancel it out, and this term basically will be 0, right. If that is 0, then I can get basically du is equal to Cv dt. That means that what you call internal energy for an ideal gas is independent of pressure and volume. It is only dependent on the temperature, right. That we have already seen. Now, we have proved that by this expression. So, in the similar way, we can look at the enthalpy change, and we will be following the similar procedures, right. And let us consider a relationship in the form the enthalpy is a function of T and P, right, and we can write down dH is equal to dou H by dou T, and for a constant pressure into dt, dou H and dou P for constant temperature into dP. And we can write down in the Jacobian forms in the similar manner, and dH is equal to T ds plus V dP, that we know from the expression. And we can write down that Hp, that is Jacobian Hp, keeping the pressure like as a variable, is equal to T in Jacobian Sp plus V into Jacobian Pp, and of course, Jacobian Pp is 0. So, therefore, you can get this is equal to T into Jacobian Sp. And we can also write down similar way, like of course, the T as a variable, and Jacobian St is equal to T Jacobian St plus V Jacobian Pt. And equation 1 you can write down in this similar form, like and then we can notice that Cp is basically T into Jacobian Sp with respect to Tp. So, therefore, this form I can write down as Cp, and we can use the what you call Maxwell relationship, right, and we know that Maxwell relation Ts is equal to P equal to Jacobian Ts is equal to Jacobian Pv, and by that we can also find out this beta as is equal to 1 over V Vp into Tp, beta is equal to 1 over V Jacobian Vp with respect to Tp, and which is nothing but in 1 over V into Jacobian St by with respect to Jacobian Tp, right. This we are getting with by using the Maxwell relationship, and substituting these things in the expression, we can get dH is equal to Cp dt into V minus beta Vt into the dP. So, that with this we can get basically the enthalpy change can be expressed in terms of what we call all measurable properties, right. And we also look at another this thing what we have already discussed, that is Joule-Thomson coefficient, right, which is a isenthalpic process, and which we have seen earlier, like which you use in your what you call air conditioning systems and capillary tubes and then porous plugs kind of things. And we know that if we will apply this first law of thermodynamics for this control, volume systems, we will find that enthalpy is remaining constant, right? And this process is known as isenthalpic process, right? Which we have already derived this thing. And if you look at that, this, like mu Jt, what we derived, that is the Joule coefficient, is nothing but dou T by dou P when enthalpy is remaining constant, right? And this region is basically the mu Jt when greater than 0, and that is known as region of cooling because of fact that when P is less than Pi, right, all the time it will be, because exit pressure will be lower than the inlet pressure, otherwise there won't be any flow, right. So then Te will be less than Ti, because this will be what you call negative in the numerator. So whereas the Te is less than Ti will be to make it what you call greater than 0, so that there will be cooling region, and similarly when mu Jt is less than 0, there will be heating region. We have already discussed this thing. Now what we need to do, this Joule-Thomson coefficient, we need to what you call express in terms of properties, right? Because it is a very important parameter which is used for design of air conditioner and refrigeration system. So therefore we need to look at it, and right, we can express this dou T by dou P when the enthalpy remaining constant in the Jacobian form, that is Jacobian TH with respect to pH, right. And I can interchange this one and then get this expression, right. And we know that dH is equal to TdS plus VdP, that we know very well. So I can write down enthalpy, with respect to P in the Jacobian form as shown here, and which is equal to basically T into Jacobian SP. And similarly, we can have Jacobian with respect to temperatures, like as a variable. So therefore, we can express this term as basically, T into Jacobian ST plus V Jacobian PT divided by T Jacobian SP, right. So if you look at the earlier is all measurable property was there, but now entropy has entered into pictures, which is non-measurable. So we need to eliminate that. So for that we know that thermal expansion coefficient beta, which is 1 over V Jacobian Vp with respect to Tp, and we know also the Cp, that is equal to T Jacobian Sp with respect to Tp. So therefore I can write down Cp Jacobian Tp is equal to T into Jacobian Sp. And with Maxwell relationship, we know that Ts is equal to Jacobian Ts is equal to Jacobian Pv. So therefore we can utilize this one, right? And so we can write down basically this as the Maxwell relationship is T into, in place of St, I can write down basically Vp from the Maxwell relationship, right. By using this Maxwell relationship, I can write down Vp here plus V into Jacobian Pt divided by Tp. So if you look at this expression becomes, like this, and then I can look at this Vp and Tp is nothing but your what you call coefficient of thermal expansion coefficient. So, in place of this I can write down as beta V, right. And similarly Pt by Pt, so therefore this will be 1, I can say Vp, and then Joule-Thomson coefficient will be equal to 1 over Cp. I can take it out, then it will be beta Vt minus specific volume, right. So, it is a, if you look at all our measurable properties, and you can get this very easily. It is not a differential, rather it is all our measurable properties. You can find out Joule-Thomson coefficient very easily. We know that beta for an ideal gas 1 over T, so Joule-Thomson coefficient will be equal to 0, right. So, if you look at we have seen the phase change processes, from the liquid to the gas, and liquid to its vapor, right, and also solid to liquid, all those things we have seen. Now, and we need to express H in terms of measurable properties during a phase change, right. And for that we will have to look at the phases, how we will express this H in terms of measurable properties. For example, heat of vaporization, whenever it is vaporized we need to express in terms of measurable properties. So, let us consider a single component system with 2 phases, liquid and vapor, in the state of equilibrium. When it is in state of equilibrium, it will be basically in thermodynamic equilibrium, that means mechanical equilibrium, thermal equilibrium, phase change equilibrium, also the chemical equilibrium, all those things will be valid. And what we will do, for example, we will take this phase diagram. I am taking because solid, vapor and liquid you can describe in a single 2-dimensional plot PT. So, if I consider this is a point here, right, and what is that? This F1 is a state where the properties of the liquid, and here the properties of the gas, right, and all will be same like at that point. And similarly, let us say at station 2, like which is another point, that also can be same. So, like that has to be maintained. As a result, the change, phase change, right, to have a phase change, the change in the Gibbs free energy will be equal to 0. So, therefore, we can say phase transition from liquid to the gas, right, will give the condition that Gibbs function, like at station 1 for the liquid is equal to Gibbs function for the vapor, its vapor at the station 1. And similar way also we can write down at this another point, like, okay. So, that is GF2 is equal to GG2. So, we know that for the liquid phase GF2 minus GF1, right, is equal to SF dt plus Vf dp. So, if you look at, there is some change in the temperature here between these two. This is basically dt, and if you look at, this is nothing but your dp, right, change in pressure. And if you look at the vapor state, right, or the gas state, right, gaseous state, that will be Gg2 minus Gg1 is equal to Sg dt plus Vg dp. Same thing we are writing, only the we are putting one is the for the vapor and other is the for the liquid, and both the sides should be same. So, therefore, if I minus it, this equation 1 and 2, I will get basically Sf dt plus Vp dp is equal to minus Sg dt plus Vg dp, right. And this you will cancel it out because of this condition, that this condition and these two conditions. So, this will be cancelled it out. So, if you look at, if I can separate this dp, all the coefficient for dp in one side and dt for the other side, then I can get the dou p by dou t on the saturated condition, because this is a saturated condition, is equal to change in entropy, that is Sg minus Sf is equal divided by the Vg minus Vf, right, is equal to what to call, that means the slope of this curve, right, this slope is equal to change in entropy, right, we are with the change in the specific volume. Now, we are in trouble in the sense entropy has come into pictures, right. So, what we need to do, we will have to use our definition of the entropy. Change in entropy is equal to change in the enthalpy divided by T, right, and then I can write down HFG by T. So, if I put this thing here in this expression, I will get dou P by dou T is equal to HFG by T VFG, right, and this equation is basically says you, like the from the slope, if I know the slope, I can evaluate HFG very easily, right, and provided I know the change in the specific volume, right, because I know this pressure and temperature, right, so that I can have conduct experiments and then find out this thing, and then we can evaluate HFG. And this equation is known as the Clapeyron equation, right. This equation is known as the Clapeyron equation, which will relate this heat of vaporization, sublimations and others also, right, into the measurable properties, right. So, of course, as I told, this is applicable to any change process at a constant temperature and pressure, because it is once pressure is constant, temperature is constant, that way see. But for the solid and liquid, or the solid as a vapor, the change in enthalpy or the heat of vaporization or heat of sublimation, right, will be always will be positive. So, therefore, what you call that if it is dou P by dou T is positive, right, and although we have seen that the change in enthalpy will be positive, and of course, then this term will be positive only if the delta V will be greater than 0, that is the expansion, right. If solid is converted into liquid, let us say, right, okay, or it's vapor, right. So, what will happen? That will be what you call expansion, but there might be some cases where that will be contraction. For example, like your water, bismuth or antimony, like these are what you call contract, right, negative. So, therefore, it will be change in the specific volume will be negative when it is solid is converted into liquid, like your ice being floated, like ice being floated in water, liquid, which is a liquid. So, hence during melting of ice, like what he says is a negative. So, therefore, whenever increase in pressure lowers the melting point of the what to call this thing. That is the reason why you might have seen that these ice skaters, right, they press it so that there will be melting out and they can move very freely, and that process the relegation, right, kind of thing, and that is being used for the ice skaters to do that. So, liquid vapor phase transition, if you look at, like we look at solid and liquid, right, we can think of liquid vapor transition. In this case, if you look at specific volume of the vapor is much larger than the specific volume of the liquid, isn't it? For example, like if you look at liquid and steam, right. If you look at, for example, if you can look at water and steam, like water, steam specific volume is much higher than the liquid specific volume. So, therefore, I can write down the change in volume during this liquid vapor phase transition is equal to the Vg, right. And if I assume that ideal gas, which need not to, but we can assume that Vg is equal to RT by P. So, if I look at then I can express dou P by dou T is equal to basically in place of what you call this expression in the Clapeyron equation. If I put this in place of what you call delta V, that became only Vg, and in place of Vg I will put RT by P, then dou P by dou T is nothing but HFG P by RT square, right. And if I can separate this thing, that is I can write down d ln P divided by dt is equal to HFG RT square, right. So, then I can integrate this equation, and I will get ln P is equal to HFG by R 1 over T plus constant, right. And then I can get this, I can plot this ln P over 1 over T, and then I can get this slope. Slope is basically this one, right. And if I plot this thing, I can get the slope, I can get also the intercept and constant. And this expression is basically known as the Clausius and Clapeyron equation. Okay. So, if you look at, I mean, you can use this thing for basically finding out the various temperatures, and if you know the heat of vaporization or these things, and it is a very useful expression relating the what you call heat of vaporization with pressure and temperature kind of things. And when you put that thing, I can get an expression like this is ln P2 by P1 is equal to HFG divided by R 1 over T1 minus T2, right. So, I can take an example just to illustrate how you can do that, use this expression for finding out heat of vaporization and kind of things. So, let us say that in order to decrease the time, right, weight placed on the steam exhaust port of a domestic pressure cooker is increased, so that it can allow the pressure to build up to the 225 kilopascal inside the cooker, and we determine the temperature at which the water boils in the cooker, and the latent heat of vaporization of water is 2258.02 kilojoule per kg at 100 degrees Celsius and pressure of 100 kPa. So, we need to calculate this temperature at which the water boils kind of things. So, how to go about it? So, if you look at what are the things are given is that P1 is given, that is 100 kPa, right, and P2 is also given 225 kPa, and T1 is given 373 Kelvin, and HFG is given 22802 kilojoule per kg, right. Of course, that is at 100 degrees Celsius and pressure of 100 kPa, right. And we will have to find T2. So, what we can do? We can basically apply the Clausius-Clapeyron equation, right, by using we can get basically ln P2 by P1 is equal to HFG by R 1 over T1 minus 1 over T2. So, if you look at in this expression, P2 is given, P1 is given, HFG given, and T1 is given, T2 is not given. You just substitute these values, right? You will get very easily that temperature T2, that is 100, is equal to HFG is given as 2258.02. And of course, this is the what you call specific gas constant. This is 8.314 into molecular weight has to be there, that is for 18 for water, 1 over 373 minus 1 over T2. So, from this you can get T2 is equal to 124.6 degrees Celsius. From this, you can get. But if you look at your steam table, right, you will get at 225 kPa, you can get temperature T2 is equal to 124 degrees Celsius, which is very closer to that, right. So, what I am saying, by this way one can know some properties and other properties can be found out very easily, and we can use this Clausius-Clapeyron equation and then Clapeyron equations, and for finding out the properties for during the phase change processes. With this I will stop over, and we have come to the end of this thermodynamic course, and I would like to quote from this Osborne Reynolds in November 1883, who says, "In lecturing on any subject, it seems to be natural course to begin with a clear explanation of the nature, purpose and scope of the subject. But in answer to the question, what is thermodynamics, I feel tempted to reply, it is a very difficult subject, nearly, if not quite unfit for a lecture." So, with this thought process, I will stop over here. Thank you very much.